Hi, my name is Tian with my teammate Wenlin here. And today we're presenting our project Fine-Grained Typhoid Image Classification. Image classification has come a long way in the computer vision field. We start with vanilla CNN to huge and deep models like ResNet, GoogleNet, DenseNet, and now even moved to Vision Transformer. But we're mentioning this because we are going to borrow some of these models and use that in our work. In this project, we are focusing on very specific sub-problem of image classification. Specifically, we are looking for into fine-grained food classification because we think it's very challenging. It's because the model has to learn to distinguish between visually similar dishes that differ minorly in, let's say, ingredients and garnishes. Moreover, we think that Thai cuisines are diverse and complex enough that makes this whole thing interesting. For example, we have a lot of overlap of ingredients like chili, cilantro, or all the garnishes, and it should be very challenging for model to discriminate those features, and that's even true for humans. For example, we have these two vegetables here. We have bitter melon leaves versus morning glory. If you look at those colors, they are both green. The soups are both dark color. If you look at the texture, they're both leafy. They have soft stems, and the soups are watery. So you can see how it's difficult for models to differentiate, and it's a challenging problem for us to solve. And it's even worse. We have Kway Chap and Kway Teow Reo. To be honest, I think it's very hard even for me to distinguish them. They're both dark color soup. They have meat. They have cilantro on top of it. They have they use the same white bowl. They look very similar, but it's a job for a model to learn how to differentiate those two. So let me talk about some written works for our project. So first, we're gonna talk about DenseNet, where each layer is connected to all the subsequent layers in the feed-forward fashion. This will allow direct feature reuse, and it will reduce the number of parameters and leading to better performance with fewer computational resources. And the second one is a ResNet, where we enable the network to learn all the residual functions instead of the traditional feed-forward functions. The model we use is a Swin V2, which is a transformer-based architecture model for computer vision problems. It uses shifted windows in a hierarchical transformer design to lower the computational cost of self-attention. The last model we use is the VG16, which is another deep network that consists of 13 convolutional layers plus the 3 fully connected layers. Our custom model is based on this VG16 architecture.
So next, we're going to talk about our data set. For this project, we use a data set of 15,770 images of 50 famous Thai dishes. And for the pre-processing, we calculated the means and standard deviations of all the training images to normalize all our data. And for the data augmentation, we decided to use the random resize crop and the random horizontal flip on our training images to train our models. And while working on this project, we did a lot of different experiments, and we learned a lot from this project. And here is the experiments that we have done and the results that we got. So first, we decided to implement a custom model just to understand better how the deep neural networks do the image classification tasks. So we decided to base our custom model on the VGG16 model. For this model, the highest accuracy that we have achieved so far was 59%. But after that, no matter how long we kept training the model, the performance just got stuck around 55% to 60%. And we also did 2 different variations of transfer learning. First, we tried doing the transfer learning by training only the final layer, and the accuracy got stuck below 60%. So then we decided to try training the entire model. And with this, we achieved the best performance. And on this slide, we can see the model performance of all our 4 models. And for the custom model, we can see that the test accuracy we achieved was 59.14%. And for the ResNet 50 model, we achieved a better test accuracy than the DenseNet 161 model, which was 80.5%. And the DenseNet model, we achieved a test accuracy of 73%. And the Swing V2 model achieved the best performance, which was 92.92%. And we used GradCam to visualize the attention maps of all our models. So GradCam was developed as a method for creating class activation maps for deep neural networks with the goal of highlighting the portions of an image that are most essential for the network's prediction. So here we can see some images of the results that GradCam gave us. And here we can see what our models are paying attention to on the images that they were given.
That our best performing model, the Swing V2 model, on Hugging Face. You can see, you can reach it by this link over here. And it has this inference section where we can run model inference easily. For example, I can go to fried chicken image and let the model predict, and it's fried chicken. So we got it correct. We can do dumpling, and the model predicts dumpling with a very high confidence. We also have some incorrect classification going on. For example, this is supposed to be Masaman guy, but the model predicts it has to be something else. As yeah, a couple more prediction examples, Gangjut. And we even pushed the data to the Hugging Face repository. You can see there are some example image here. So you can preview on those train, test, and validation data easily. Yep, that's it. Model and the data repo. Thank you.